Hey everyone. So in this video, we're going to understand what the cross entropy loss is, what the math behind it is, and how we can implement it quickly in Python. Why are we doing this? Well, in this series, we have been learning how we can build neural networks for classification, and we're using an email classifier as our example. So we've figured out what the neurons are, learned how to assemble them into layers, and then after the layers, we now have a final layer, which is the softmax layer, right? Which takes the output of the last hidden layer in the neural network and converts it into probabilities, right? So the last hidden layer in this case would give you, for example, if you had three classes and you were trying to predict what class the email, which is our input, belongs to, you would have three layers, three neurons in the last layer. But what it would give you would just be numbers, right? And so to make sense of that, you would use the softmax, which would then convert that into probabilities. But that's great. How do you know your network is accurate, right? So what we need to do is take data and train the network on that. And so to train it, you need to figure out the error, in the prediction of the network. And then also get the sensitivity of the error or the loss in the prediction with respect to the parameters of the network, which are the weights and the biases of these neurons, right? And then using gradient descent, you can train this network. So what we're going to focus on in this video is this error prediction methodology using the cross entropy loss. So we've used this example in the previous video as well, but let's say we have three classes that we're trying to classify the input into. In the actual final example, when we get to that, the full network, we'll have six classes. But in this case, let's say the email can be classified as important, marketing, or spam, right? And let's say the softmax, and we've used this example in the previous video on softmax. Let's say we have the probabilities coming in or coming out of the network, let's say, to be 0.18 for important, 0.31 for marketing, and 0.51 for spam. And we're going to call this predicted value of the network y hat. Okay. Now, what do we have? Well, this is our data we're training the network on. So we also know what the email actually is, right? In this case, it's spam. So we're going to write that as a vector here where you're going to say, well, it's not important. So that's 0. It's not marketing, 0. And we know it's spam, so 1. And we're going to call this y. So the label is y and your actual predicted value, or rather your predicted, not actual, your predicted value is y hat. Right? And we need a way to now find the error in the predicted value given the actual value. Right? So what we're effectively doing is the softmax is giving us probability. So this is a probability distribution. And so is this. And we need to find the error between these. Now we've written the label, right? Or the actual, the actual value in a form, right? 0, 0, 1. So what does that mean? Well, this is called the one-hot encoding, right? Which is a way of representing the labels. So what does that mean? Let's look at that quickly. We know the output belongs to one of these three classes. So we can say class 1, class 2, and class 3. 1 is important, 2 is marketing, 3 is spam. But the neural network with the softmax is actually giving us not a value, right? It's giving us probabilities, 3 probabilities for each class, 1 for each class, right? So we need a way to compare that effectively. So what you can do is then say, well, suppose in a different case, this was the marketing was the actual email, right? So it belongs to class 2. You can write the output, the actual label as a vector, right? And you can say, well, it's class 2. So this one, class 1 is set to 0. Class 3 is set to 0 because it's not those two. And the value that's the actual value, right, of the label, this 2 is set to 1. So that is the hot value. So the value that the actual label belongs to is hot. And so it's 1. The others are cold, right? They're 0. So they're set to 0. And this way of representing which class the actual data belongs to is called a one-hot encoding. So this is for each data point, you can actually compute this. Let's look at an example, right? A few examples rather. So let's say you have this email that is win a free iPhone 14 by clicking this link now, right? It's a spam email. We know it's been labeled spam. So the class is 3. So you're going to write it as 0, 0, 1, right? And this, if you write it, you'd write it as a vector. But in this case, I'm just showing you in tabular form. What about this one? Exclusive offer, 50% off. It's a marketing email. So it's class 2. So you'd write it as 0, 1, 0. What about this one? It says flight change alert, your departure time has been updated. That's an important email. So class 1, so 100. Another one, don't miss this. Your favorite brand sale ends tonight. It's a marketing email, class 2, so 010. So this way you can take the output label, whatever class it belongs to, and write it in this one hot encoding form. Okay, so now that we've understood that, what is the problem we're solving in this case? We're saying we have the predicted set of probabilities for the classes, and you have the actual label. In our case, the third one is the correct one. It's a spam email. Now, what we want to do is minimize the error, right? So to do that, we compute the loss. And so what we're going to do is for this, and this is for each data point. So then you would have to sum across the data points as well. But for each data point, what you do is say, well, I have the predicted values in vector form. I have the actual label. What I'm going to do is say, well, take yj, which is each element, which of the label, multiply that by the log of the predicted value y hat j, then sum across each element, right? So 0, right? And then what you do is take the negative of that, and that will give you the categorical cross entropy loss or multi-class cross entropy loss. And then if you sum across each of your data points, you get the overall loss for your data set. So let's do an example. Let's take this data point. Well, what you'll have here now is 0 times log 0.18 plus 0 times log 0.31 plus 1 times log 0.51. So 0 times something is 0, 0 times something is 0. You're left with this term. Log 0.51 is minus 0.29. But now you also have a minus 1 being pre-multiplied by it. And so the answer becomes 0.29, which is your loss for this predicted and actual label. And that's it. We've got the NN Cross Entropy loss. But that's not where we stop, right? We've got the loss, but what's exceptionally important is to compute the sensitivity of the loss. And what we'll do first is compute the sensitivity of the loss with respect to the inputs, right? And then we can use backpropagation to push this further back down the net. So two sets of inputs to the cross entropy loss is the label y, and then the actual value or output of the neural network, which is, in our case, the output of softmax, which is typically what is used, which is y hat. Now, we don't care about the sensitivity with respect to the label because the data is the data, right? What we want is the sensitivity with respect to the output of the neural network, y hat, and then that can be further propagated back. What we want is the partial of the loss with respect to y hat I, right? Meaning each component of y hat for that data point. So that's dou by dou y hat I of this term. The negative can be brought out. And now we know that yj and y hat I, there's no dependency, right? But actually first, before that, actually a different step. Let's expand this sum, right? So j equal to 1 to n is basically y1 log y1 hat plus y2 log y2 hat plus and so on, yi log yi hat plus all the way to yn log yn hat, right? Let's say there are n data points. Now, where is the dependence? There's no dependence on y1, on y2 if you're differentiating with respect to yi hat. Only dependence is in this term, right? Dou yi log yi hat by dou yi hat. All the other terms are not dependent on yi hat. So all the other terms go away, and this derivative reduces to minus dou by dou yi hat of yi log yi. So if it was y1, it would be dou L by dou y1 hat is dou by dou y1 hat of y1 log y1 hat. If it was y2, the same way, and so on. Now, there's no dependence on yi, so that is taken outside the derivative as well. You get dou by dou yi hat of log yi hat. The derivative of a log of something is 1 by that something. So what you end up with is minus yi by yi hat. So the sensitivity of the loss for one data point with respect to a corresponding element of the predicted input, right? The output of the neural network, which is the input to the softmax or to the cross entropy, is the label of that element yi by the actual predicted value. Right? Now, in our case, we're using a one hot encoding. So what happens in that case? Well, so for our example, let's say you have 3 elements or 3 classes. You have 0, 0, 1. Well, what would happen? So for these two, the numerator, which is the actual label, would go to 0, right? So dou L by dou yi hat, right, for the corresponding yi equal to 0 would go to 0. And when the yi, the element is equal to 1, it would be minus 1 by yi. That's it. So it simplifies even further, right? So in our case, this one is 0. So dou L by I hat for the first class is 0, for the second class is 0, and for the third it's 1 minus 1 by 0.51, which is minus 1.96. And that's it. That's the sensitivity of the loss function for this data point with respect to the outputs of a neural network, right, which is predicted using softmax. Now, given softmax and the cross entropy loss are typically used together, we can come up with a sensitivity that combines across this. So what you do typically, what you could do is take the derivative for the cross entropy loss. You have the derivative here, and you can chain, right? Use chain rule, and you get the value, which is what we'll do. But it simplifies to something simpler. Now, one way to get that simplification is you could just take this, and this is y hat, and substitute here, right? But we'll not do that. It's a the derivation can get complicated. We'll just see what happens. So in the previous video, we've already derived the sensitivity of the softmax, right? We know the Jacobian, the sensitivity of an output, and in that case, we called it AI with respect to an input Z, Zj, and the softmax has n inputs and n outputs, is AI 1 minus AI when I equal to J, right? So the diagonal terms. And for the off-diagonal terms, when the I is not equal to J, it's minus AI Aj. And we've done this in a lot of detail in the previous video. Now, for the cross entropy, we know it's dou L by dou yi hat is minus yi by yi hat, right? And for the one hot encoding, we know it simplifies. Now, to kind of show you the notation, the AI, which we did in softmax, the output there is the input to the cross entropy. So yi hat can also be called AI. And so I'm going to use AI here. So it's minus yi by AI, right? Okay. So now what we can do is use chain rule. Say the sensitivity of the loss with respect to a input to the softmax, not to the cross entropy, the input to the softmax. Dou L by dou Zj is, using chain rule, the sum of dou L by dou AI times dou AI by dou Zj. And you sum that for each of the AIs because the dependence comes through each of the AIs. You sum that. So we can write this in a matrix vector product form. So for our example, let's take three classes. So you have dou L by dou Z1, dou L by dou Z2, and dou L by dou Z3 for our three classes. We've just derived this, we've just shown this formula before. So you'd have the diagonal terms being A1, 1 minus A1, this is A1, I'm sorry, A2, 1 minus A2, and A3, 1 minus A3, and the off diagonal terms, right? And this is the softmax Jacobian. And then we have the loss of the NN cross entropy. I've used the one hot encoding, so it's 0, 0 minus 1 by A3, right? Which is what we have previously. And now what we can do, it's just that I haven't used values. I've just used the fact that it's A1, A2, and A3, which are the outputs of the softmax, right? So if you do this multiplication, what do you get? So if you multiply this with this, these two terms are multiplied by 0, you get minus A1, A3 by A3. This again, 0 minus A2, A3 by A3. And then here, these go to 0, and you get A3, 1 minus A3 by A3, and there's a minus. And that's the sensitivity. So that is basically dou L, dou Z, right? You can simplify this, cancel the A3s and the negatives, you get A1, cancel the A3s and the negative, you get A2, and here cancel the A3s and you get A3 minus 1. So it simplifies to A1, A2, and A3 minus 1. So you see that the sensitivity of the loss function with respect to the inputs to the softmax, not the NN cross entropy, are actually very simple. It's the output A1 here, the output A2, and then the output A3 of the softmax minus 1. So rather, from the context of the cross entropy, these are the inputs to the cross entropy. And it's just the sensitivity of the loss with respect to Z, right, is just A1, A2, and A3 minus 1. Now, why is this A3 minus 1? So if you had used the actual derivation where you had substituted this value of A or Y hat in this and differentiated, you'd see it. But to simplify it for you, we can break this into two parts. We can say A1, A2, A3 minus 0, 0, 1. Now we know 0, 0, 1 is our one hot encoding of the label, right? So what we have actually, and this is what you'd get when you derive it, and I'll add a link to the derivation, right, is A1, A2, A3 minus Y1, Y2, Y3, which is the elements of the label, right? Which is what this is. And so in a more general way, the sensitivity of the loss with respect to Z is basically just A minus Y. A is the output of the softmax, which is the probabilities predicted, minus Y, which is the one-hot encoding of the labels, or rather just the labels. Right? And so you get, instead of doing the chain rule and multiplying, you can actually just find the sensitivity of this expression in one shot, right? It's just A minus Y, get the output of the softmax, subtract from that the one-hot encoding of the labels. So in our case, 0.18, 0.31, and 0.51 minus 0.001. And so dou L dou Z is 0.18, 0.31, and minus 0.49. So that's quite simple, right? Great. So this is typically what you do for a loss function in a classification problem. You typically have the softmax as the last layer, and you have the NN cross entropy or the general cross entropy as the last, or rather the loss function. So now what we'll do next is just go and code this up. Okay, so we've opened up our Jupyter notebook. Now this is the same notebook we've used previously in this series. So we have a tanh neuron, we've assembled that into a layer, and then we've got the softmax function, which we've previously implemented. So that takes in the input X from the previous layer and gives you the output of the softmax and also the sensitivities of the softmax function. So now what we're going to do is implement the cross entropy loss. So I'm just going to copy paste this quickly, and so we're going to say, well, cross entropy, and it's a very simple function. It takes in y hat, which is the output from the softmax, and y, which is a set of labels, one hot encoded, and loss is np dot y, np log y hat, which basically does sum yi log y hat, right, where I is each element. So taking a dot product, as you know, basically just does that, right? It does this operation. It takes each element of this and this. So this is log y hat, y, it takes each element and just multiplies that, right? And then adds them up. And then we know the sensitivity of that is minus y hat, right? We've already done this in the theory, so we know that as well. And we return the loss and the sensitivity. So actually that's all. That's the implementation. It's really simple. So let's set up the inputs that we're going to give it. This is similar to the previous example. These are the inputs we've used here for the softmax as well. So we're being consistent. And then the labels. So let's run that. And then what am I going to do? I'm going to say okay. So we'll initialize the softmax layer. And there's a reason for this. And the next we're going to implement the combined softmax plus cross entropy. So we're going to initialize the softmax and the cross entropy. And then what we're going to do, so it says softmax layer is not defined because I've set it up as softmax, right? So let's just call that. And cross entropy, oh, I haven't run this. So let's go back and do that, okay. And then what do? We first run the forward pass. So we have to run the forward first through the softmax. So we take X, right, which are the logits from the last hidden layer of the neural network, let's say, passed into the softmax. It returns the probabilities, and then we pass that, so the set of outputs of the softmax, which is A, and the labels, into the cross entropy. What we get is the loss and the sensitivity of the loss. And so we see the values 0.18, 0.3, 0.506. In the theory, in the slides, we rounded this up, and then we also see the loss 0.68. And if you remember from the slides, we had these values, right? And that's it. That you've got the forward and the backward through the cross entropy loss. Now what we'd have to do, right, is now pass this back through the softmax to get the sensitivities, right, of the with respect to the softmax. So let's go do that, and now you get this, which is basically now taking the LDA that the cross entropy loss is returned, passing it through the softmax, and now what you get is a sensitivity with respect to the inputs to the softmax, which is the outputs of the last hidden layer of the neural network. and we've got these values, and we've seen this again in the notes, right, or in the slides. So that's one way you could handle this, but we've also seen that there's a simpler way to implement this. So let's go implement the softmax cross entropy loss, I'm calling it, where what we're going to do is we're going to take in Z directly and the labels. This is the softmax, so the numpy dot exp is the numerator of the softmax. You sum that up, and that's the denominator. And so you get the softmax output here, the A's, right? And then the loss is the same, right? It's just, NP log A and NP dot sum. You can also use the dot product as I've used above, right? Just two different ways of representing this. But now the sensitivity of the loss is now not with respect to the inputs to the loss function. It's actually with respect to the inputs to the softmax, is A minus Y actual. A is the output of the softmax, which we have computed here locally. Y actual are the labels. So what we do now, as you can see, is so much simpler. We've got the input and the labels, X and Y, exactly the same as above. But now what we can do is, instead of using the softmax, doing a forward pass through the softmax, then a forward through the loss function, and that gives us the sensitivities, then backward through the softmax again. It's just one evaluation. We pass in X, which is the logits coming into the softmax, and Y, which are the labels, and we get the same values as we did above, but now in a simpler operation. And what we get here is not this, which is the sensitivity of the cross entropy with respect to the inputs of the cross entropy. We actually get this dl dz directly. So that's that. It's as simple as that. And now you know how you can implement the cross entropy loss function for a classification problem, and you know how to use it in conjunction with the softmax. Okay, so let's now go back to the slides. Okay, so we have in this series till now got the neurons assembled into layers, got the softmax, and now we figured out the loss function, the cross entropy loss. What is left now is figuring out the input, right? We're saying we are feeding in emails, but we're actually going to be feeding in numbers, right? So how do the email become these numbers? How does the email become a vector? Well, we use a vector embedding methodology. So in the next video, we'll review that fairly quickly so that you understand what kind of data we're using. And then we can go in and assemble our network and train it and make it an app, right? So see you in the next one.